Okay, so welcome to Chem Lab, everyone. Hopefully you guys are watching this video to review for some of the material we learned beforehand. This is stuff from the first week we had practice, and mainly I'm just going to be once again reviewing the format and some of the more simple stuff that we have learned. So the format of the test is just a 50-minute test you're going to have. The event is 50 minutes long. It's going to cover both a test portion and a titration portion that you're going to have to do there. And basically what you're going to need to be able to do is, name compounds, perform stoichiometric reactions, and, collect data, interpret graphs, diagrams, and obviously you're going to be needing to know how to do a titration. So specifically this year's topics are aqueous solutions and redox reactions, which touches on electrochemistry as well. And aqueous solutions, that's kind of a broad topic that could range from acids and bases to equilibrium to like KSP and other related topics, dissolution. So for this tutorial or this kind of walkthrough, I'm mainly just going to stick with some of the basic things that every chemistry student should know, and we're going to start out with just some simple atomic structure and periodic table. So the atomic structure, I'll just write that over here. Sorry, I'm kind of new to this stuff. So atomic structure is basically in an atom, it's consisting of a nucleus and a electron cloud. So this nucleus is kind of like the center of the atom, and the nucleus contains protons and neutrons. So as the name suggests, protons are positively charged particles, and neutrons are neutrally charged, meaning they don't actually have a charge. So if I wanted to start drawing out a atomic structure, I would have that's the wrong color. Let's change the color to something like that. So say these are protons and they're joined using the weak nuclear force with neutrons, which are in white, and this is the nucleus. So, and then we have this electron cloud also present, this electron cloud. Now this electron cloud is basically not necessarily one cloud, it's like orbitals or kind of like shapes that electrons, which are negatively charged particles, move around in. And obviously this is not the correct representation of what the electron clouds look like. Getting into more AP chemistry and higher chemistry, you'll learn that it's more shells, and there's a lot of like probability involved, and like quantum mechanics involved with where you're going to find an electron in a certain portion of the atom. But for right now, all we need to know is that the electron is kind of near the outskirts of the atom and kind of revolve around the nucleus, just like that. Alright, and so the number of protons is most necessarily equal to the number of electrons, so I'm just going to write Ne minus is equal to N. I just want to color code this. Ne minus is equal to Np plus, and E minus just stands for electrons, and P plus just stands for protons. And this is most likely always the case, except for when it is an ion. So not ion, or it's in its molecular form. So there's another thing that we should definitely go over, and those are called isotopes. So isotopes, I'll just write it down over here. Isotopes are basically when there's a difference or there's a change in the number of neutrons that are present. So change in number of neutrons. And this changes the mass of the atom, because let's also go over atomic weight. We have weight is equal to the number of protons plus number of neutrons. And why this is because the nucleus itself makes up about like 60 to 80% of all the mass in the atom. So the electrons have negligible mass. So the weight is mainly determined from the number of protons and neutrons present in the nucleus. So, for example, something that many of you may have learned about is the carbon isotope. So carbon is a very strange element in that it can be present in multiple different types of isotopes. The most common is the difference between carbon-14 and carbon-15. This mainly means that there's one more neutron. Okay. So now I'll just clear the board. So now we can talk about ions. So ions, I know I briefly mentioned that when I was going over atomic mass. So ions is basically the number of protons, or the number of protons and the number of electrons are not equal. And this results in a charge. And charge is mainly dependent on the number of electrons there are in a certain atom. So let's say I have element X, and it initially has n electrons, and it has n protons. But say we lose one electron, so now we have n minus 1 electrons. So this might be a little bit of a harder thing to understand, but the only thing that is ever gained and lost in an atom is the electrons. I mean, obviously isotopes have a different number of neutrons, but in the bonding sense, the only thing that will ever be lost is electrons. So if I have one less electron, that makes this into X plus, because now we have less negative, right? So it's less negative, which would mean it's also more positive. So we have it's an ionic form with a positive charge. So we call this a cation. And cations have positive charges. However, let's say that we have n electrons and n protons to begin with, but then we have n plus 1 electrons. And we still have n protons. This means that X becomes X minus because it became more negative, there's a negative sign over here. So it's more negative. So this is called an anion. So a way I like to remember it is that anion is similar to onion, and if you're cutting onions, they make you cry, which is a negative thing. So anions are negatively charged. Alright. Obviously everybody has seen a periodic table. I don't really feel like drawing one out. It's mainly because I'm lazy. But generally this is the idea of the periodic table. It's just a bunch of stuff here. And then we have some stuff here. Like that. And then we have some random crap over here. And that's your periodic table. So when you're looking at an entry in the periodic table, it'll usually look something like this. We have an element. Let's have the symbol be 8 or X. And then it'll have the number over here, atomic number. So this atomic number shows the number of protons. And then it will say the name over here. And finally, it'll have the weight down here. So, if something that you should be able to understand is if we have the number of protons and the weight present, we should be able to solve for the number of neutrons. So we would just have to set up that weight is equal to NP plus N, and then NN is equal to W, which is weight, minus NP. And you can solve that. Okay, I'm just going to clear my board again. So now we can also talk about some distinctions between periodic tables, like the elements on the periodic table. So I guess I ended up drawing it anyways. This is our periodic table. And it's a rough drawing. Please don't judge me for my drawing. I don't want to put up a real periodic table, and this is the easiest for me to do it. So metals and nonmetals and metalloids. Metals, non-metals. So metals, you'll see metals. I'm just going to color code it with positive or with red, because red means positive, and usually metals have cationic form. Metals are mostly will be present in this area, whereas non-metals will mainly be present in this area. And then we have this weird space over here that I purposefully left out. That's over here. This is the region of metalloids, where it could kind of be both a metal or a non-metal depending on different properties or different surroundings. And then we have some weird stuff down here. I think they're called actinides, and I don't know, something else. I don't care. It doesn't really matter. So that was just, I mean, you want to take that in, that's fine. It doesn't really matter much given the scope of like what we have to do in this event. So I'll just clear the board once again, and then we'll talk about valence electrons. So valence electrons, let's go over a bit about what we had talked about before with how the atomic structure is not necessarily what we determined it to be. So say we have our nucleus, which is mainly positive dominated, with some sparkle of neutral charges. So then what we have is just, instead of it being clouds, we have shells of electrons. So for example, let's say this is a, well, there's 1, 2, 3, 4, 5, 6. There are 6 protons in this. So if I were to pull up a periodic table and just look up which element has 6, you should probably know this. I'm kind of being dumb right now, but let's say this is a 1, 2, 3. This is a carbon. I did this on purpose. This is a carbon molecule or a carbon atom. And so for this one, there's a general rule that electrons will kind of occupy each shell in different amounts. So for example, this first shell can only take 2. And then the next shell can only take, I think, 8. Or sorry. Yeah. Next shell can take 8. The next shell after that can take 1, 2, 3, 4. It can just generally take more. I don't know. So the equation is 2n squared. So this one will go to like 16 or something. But what I'm trying to say is if the carbon atom has 6 protons and 6 electrons, these electrons need to be added into the shell accordingly. So if the first shell can only take 2, we're going to add 2. 1, 2. So we subtracted 2, so we have 4 electrons left. And now these electrons, since the space for this is 8, it's more than enough. So carbon will only have 2 shells, and its outermost shell is very important. The outermost shell is this shell, which has 1, 2, 3, 4 electrons. So the valence electrons are the outermost shell, and electrons, it's the electrons present. And why it's important is because valence electrons are the electrons used to bond with other atoms. And why is that? Since it's further out to the nucleus, there's less of a force acting between this and that, which is actually a Coulombic attraction between the positive and negative. Since there's more distance between it, there's less of an attraction, so it's easier to leave that subshell and either be transferred or be shared between 2 other subshells, which would either result in an ionic or covalent bond. So in this case, carbon has 4 valence electrons, meaning 4 electrons it could either donate or share. And we would draw its Lewis dot diagram, which is a way to signify how many electrons carbon has. And this would be the Lewis dot diagram. So the octet rule is something else we should talk about that pertains to this topic. The octet rule is kind of basically that electrons or atoms want to get to either 0 electrons in their outermost shell, which would mean they have a full shell. That's the next shell, which would be its last shell after that, which is a little bit confusing to understand. Or it wants to get to 8 electrons in outermost shell. Okay. So with this, I'll stop there. Some quick things that you may need to memorize or understand is with the atomic or with the periodic table, there are some trends that you should probably understand, and that is those are called periodic trends. So if this is your periodic table, you will see your atomic radius, which I will color code as red. Your atomic radius. Okay, excuse me, but this is red now. Atomic radius will increase as you go up in the periodic table, and it will also increase. Oh, I'm doing this wrong. Atomic radius will, I apologize for this. Atomic radius will increase when you're going down and when you're going to the left. So this is your atomic radius's trend. So generally, this is the direction that atomic radius increases. You also see Z effective. So Z effective is the effect of the positive charge of the nucleus on the valence electrons, and it increases when going across the periodic table because the pull from the protons increases. And so, but it doesn't change when going down the periodic table because the number of protons and electrons is increasing, but the distance between the protons and electrons is also increasing. So overall, it stays the same. So another thing that you may need to understand is the ionization energy, and the ionization energy is just a fancier term to say that the energy needed from one electron to jump from one shell to another, and therefore it creates an ion. So ionization energy has this trend where it increases going up and to the right, and yep, that's ionization energy. There's some funky stuff that goes on in this area with the ionization energy, but we're not really going to go into that. So why does it increase when you're going across? Because of the Z effective. It's increasing as well, so both of them are going to increase. And it decreases going down because there's an increasing atomic radius, so it's harder to really pull it apart or jump it to the next level. And there's the last thing that we're going to need to know, and this is electronegativity. Now, electronegativity is a pretty important topic. It's basically the ability of an atom to attract electrons, and because it's going to increase when going across the periodic table, similar to the ionization energy, and this increases because of a stronger Z effective, and it's going to decrease when going down, which means it's going to increase when going up. And why does it do this? It does this because there's an increasing distance between electrons and the nucleus. So those are your main electronegativity. Those are your main atomic things that you're going to need to know for this event. There's not really much else you're going to need to know. Definitely check out some naming, naming practice with ionic compounds, covalent compounds, how you'll name their molecules, and how exactly they bond. I will hopefully make a video on that soon as well. But really, that's all you really need to know on that stance. Okay. How do you exit out of this thing?